Hello, this is Garth Wiley from 6DOF Testing and Analysis. Today we're going to talk about product structural validation, particularly from a rotating machinery systems approach. And the material we're covering today is heavily weighted by our experiences over the years, particularly in reciprocating types of rotating machinery. In a previous video, we had discussed a number of different validation approaches. Depending on the different products that could be involved, their applications, there's different approaches that can be used. Here we're going to mainly focus on rotating machinery systems and show some examples of how we can partner with our customers, providing training and so forth. All of this is heavily oriented and influenced and guided by the simulation activities, and our approaches essentially have a strong integration between testing activities and simulation activities. We will be discussing the types of simulations that we do, linear vibration, torsional vibration. We'll be discussing the types of testing that we do, what we call modal testing and operating testing, and how we evaluate the results of these tests to come to a final validated design. In the simulation world, there are two types of simulations that we mainly get involved in. One is linear vibration, which is basically a finite element model, and it is aimed at determining the mode shapes of vibration, the resonant frequencies of the structure, and so forth. We also look very often at inertial G loadings aimed at getting a sense of the robustness of the structure, lifting stresses in the case of rotating systems that have to be lifted by a crane. Also, we look at the torsional vibration. And this again is aimed at looking at torsional vibration modes, pretty much with a numerical lumped mass type of analysis that will give us the torsional resonant frequencies, mode shapes, and even the forced response of the system. So the general idea here is we look at an interference diagram where we have a frequency and a RPM of the rotating machinery, and these diagonal blue lines are the strong forcing functions coming from the reciprocating machinery, and the vertical lines are maybe the speeds where it commonly operates at. And what we want to try to avoid is having a significant mode of vibration intersected by a strong order of forcing function of the unit, and that occurring at a commonly used operating speed. So by looking at these interference diagrams, the results of the torsional and linear vibration analysis, we can identify improvements simply based on trying to move resonant frequencies and mode shapes away from strong forcing functions. The validation testing usually involves modal tests, which in the case of these types of machines, we often use impact modal testing techniques, where we essentially measure mode shapes and frequencies, as well as operating tests, where strains and linear and torsional vibration may be measured over a range of speeds, loading conditions, and so forth. Both of these types of tests are heavily influenced by the simulation results. They particularly give us good locations for strain gauges and other instrumentation, and give us an idea of what particular frequencies and operating speeds we may want to pay a lot of attention to. Now, there are some alternatives to how we do some of this testing. In some cases, we essentially send our test teams on site and perform the work for the customer. In other cases, we have what we call assisted testing, and that's where we ship the equipment to the customer, and usually a case similar to this. We provide training on how to set up the test equipment and how to place the sensors. Then we can drive the equipment ourselves over the internet, looking at the response results and recording all the different files and so forth. So in this case, the customer's technicians become our hands, and we're essentially running the test. And there's some advantages of this, both in cost savings sometimes, but also in training for our customers. The modal tests are done by impacting the structure at several different locations and moving accelerometers from location to location to essentially map out a geometric image of the structure. And this data, which results in what we call frequency response functions, is then processed by algorithms within our modal analysis software that essentially produces the experimentally determined mode shapes and frequencies. The operating tests involve often running the machine over a range of speeds to identify resonant peaks and so forth, but also to take data at particular constant speeds where the machine may operate at. The validation test data is evaluated and compared to the simulation results. For example, the experimental modal tests, resonant frequencies, and mode shapes are compared to those predicted by the simulation models to determine if our initial work was accurate and essentially to correlate these models. The operating data is looked at from both constant speed data, looking at stresses and vibration levels. Often these are compared to targets. Speed sweeps, looking at the strains and stresses and vibration levels, are used to identify resonant peaks that are excited in operation. And these in turn are compared to modal test results and simulation results. Additional things are looked at as well. For example, connections in mechanical systems are often very important. Are stresses near welded joints within acceptable limits? Bolted joints can be evaluated to determine the stresses in the bolted joint connections. And again, vibration levels can be compared to industry standard targets and so forth. So both the torsional and FEA models are correlated from this test data, and ultimately the design is validated once all the pieces of this puzzle fit together. The simulation results, the modal tests, the operating results, all of this together gives us a good picture of how the structure is behaving and if we are getting good vibration results, good stress results, and so forth. So thank you for listening. Any questions along these lines, please contact 60RF Testing Analysis at our website. Also, we can be emailed at info@60test.com, and below here is our phone number. Once again, thank you for listening.